5.2, logarithmic functions. I love log functions. It's great. It's going to be awesome. Today, we're going to move between exponential and logarithmic forms. So we talked about exponential forms last time. Today, we'll talk about how to convert those to logarithmic forms. And yes, you'll want to do that. Evaluate log expressions using basic properties of logs. We're going to graph log functions a little bit. We're going to apply properties of logs to expand and condense log expressions, which is awesome. And we're going to use the change of base formula, super useful, and solve equations with logs. Yes. Some lessons I get really excited about, and I get really excited about log functions. Oh, love it. All right. First, why do we need logarithmic functions? Well, we know that an exponential function, we talked about those last time, it's kind of like this, as an inverse function, because it is one-to-one. Now, if you don't remember what it means to be one-to-one, it means it passes the horizontal and the vertical line test. So it's a function because it passes the vertical line test. It's a one-to-one function because it also passes the horizontal line test. So we know that this function has an inverse function. To find the inverse function, you should have done this in algebra, but I'm going to remind you how to do this now. You're going to, 1, switch x and y. 2, solve for y. This is the way that you would find any inverse function, and we're going to do this for logarithms, or for exponential and logarithms. But if you were looking at something like this, for example, y equals 2 to the x. We talked about this function quite a bit in the last session. We were talking about exponential functions. If I was trying to find the inverse function for this, and I followed these rules, I would say, all right, let's switch x and y, got it, and solve for y. Then you'd be like, wait, how do I do this? How do you do this? You need logarithms. We need logarithms. Did not know you needed them in your life until today, or when you first learned about them in college algebra, but we don't have to get into that. One very important thing that I'm going to remind you of before we get going, a logarithm is an exponent. I think sometimes, because we call them logarithms, they sound really crazy and confusing, and students are like, oh, there's this weird logarithm thing, and I have no idea what's going on. A logarithm is an exponent. So let's talk about how we're going to move between exponential and logarithmic form, and talk about how we might find these exponents. Okay, so exponential form, b to the y equals x. Logarithmic form, I want you to notice the difference here. Now, this is, by the way, for a base other than e, because we talked about both of these exponential forms in the previous section. But if we had a base that wasn't e, taking the exponent, a logarithm is an exponent. You're taking the exponent and you're setting it equal to the logarithm. The base stays the same. And then your x is the argument of the logarithm. So we would say this is y equals log base b of x. That's usually how we would say this, log base b of x. Now, if we're looking at that special case where we have an exponential expression and the base is e, we would write this using a natural log. So a natural log is really just log base e of x, but because it's so useful to us in math and because we use it so often, we give it the special name ln x. So the ln is the natural logarithm. Okay, so ln is natural logarithm. that is the one that has a base of e. Now, if you write your logs with log base e, I'm okay with that. If you write them as lnx, also fine. It does not matter to me. Just make sure that you don't use a natural log when you're talking about a base that's not e, because it's specifically used with that. That notation is specifically used in the case that you have that base. All right, I feel like there was something else I was about to say. One of those like, don't do this things, but now I can't remember what it was. All right, but this is the way we change this notation. Oh, one thing I wanted to mention, I had some students last semester who told me that there was a way to remember this, and it was called like the snail method or something. I looked it up actually a couple minutes ago before I started recording your lecture, and look, I had a hard time really seeing exactly how the snail method works. But if it sounds familiar to you and you're like, wait a second, snail method, I think I learned this. Okay, so here I think was the idea. So you take this snail and you, maybe I wrote this in the reverse order. This thing is new to me. Here, I'll write it like this maybe. Get rid of this y. I think the y goes on the right to make the snail. You go b to the y equals x. So there's like a circle that goes like this, and there's a circle that it's kind of like an arc. Okay, so the arc goes b to the y equals x. Okay, even if the scale thing means nothing to you, but you like the graphic, please use the graphic. However you need to remember how to convert between exponentials and logs, do that. I kind of like the graphic, I guess, but it's b to the y equals x. The way they show it, it's like there's this, I honestly don't know. I couldn't figure out. I mean, I could see that they drew a snail around it. But if you have more information about this, please feel free to let me know. But it was like they took the snail, they put like a head on the snail, and he was like smiling, and then they were like, "There's the snail." I don't know. It kind of looks snailish, but you know what it looks more like to me? This. It looks like my whiteout pen. Maybe it's not the same method after all, it's just the whiteout method. Anyway, if you learned snail and you want to use that, that's fine. Like, I honestly just feel like they were just trying to make it memorable, so they like tried to force it into something that it didn't necessarily fit. Okay. Anyway, enough of the snail. Feel free to look it up on your own. All right, write the following in log form. 7 to the x equals 49. So we ended with the last section on equations that looked like this. We solved something that was quadratic in form, and we had e to the x equals 9. This 7 to the x equals 49. So this is your exponential form, and we're going to write it now in log form. So to write it in log form, we just need to know which piece goes where. Remember, the logarithm is the exponent. There's your exponent. That's how I know what the logarithm is. So I know I'm taking 7 to a power to get to 49. The base is 7. That's the number being taken to the logarithm. So if I know that the base is 7, I'm going to write a log base 7 of 49 is the exponent. The logarithm is equals means is the exponent. Exponent is x in this case. So log base 7 of 49 equals x. Now, the classic question I always get from students at this point is, well, can you show us how to put this into our calculators? I will show you how to put that into your calculators in a little while using something called the change of base formula, but I don't think that your TI calculator even has a way of computing a log base 7. I could be wrong about that. I'm sure that I could hand a calculator to my 4-year-old and she would somehow find the way. But I'd have to look it up. I always use change of base formula, which we'll talk about in a little bit. All right, now this one we're going to write in exponential form. So this one is going to be the natural log A equals B. And we're going to write it in exponential form. Personally, I would probably switch this over to log base e, because if you're going to write this in exponential form, it's a natural log. You know that a natural log has base e. So you might find that it's easier to write this as log base b, log base e, I'm sorry, of a equals b. These two are saying the same thing. Now, I have not actually written it in exponential form yet. It's still in log form, but these are two equivalent log forms. And now if I'm going to write this in exponential form, I'm going to take the base e to the exponent. A logarithm is an exponent. Get a. That's it. This is your exponential form. So just, I don't know, get used to doing that however you'd like. If you really liked the graphic, well, say no more. We can always put the graphic on there. It goes e to the b equals a. I think that's how the graphic is supposed to work. Look, I'm like all in the snail thing now, even though I mean, you see how it works. Evaluate. We've got log base 3 of 1/9. Yes, log base 3 of 1/9. So if you're wondering how we're going to evaluate this, if we can't do it in our calculators, well, we do have a way later that I'm going to show you how to do this in your calculator. But for now, we're going to change it to exponential form. So it's in log form. We're going to change it over to exponential form. So let's say we don't know what this value is that we're trying to find. You can call it something. You can call it x. So this is what we're trying to evaluate. If you don't know what it's supposed to be, call it x. We got to give it something so that we can solve for a variable. I know that 3 to the x equals 1/9 just by converting from logarithmic form to exponential form. 3 to the x equals 1/9. The base to the exponent is 1/9. And then I can rewrite 1/9 so that I have the same base on both sides. This is what we did in the end of the last section. So I can write 9 as 3 to the -2nd power because it's 1 over 3 squared, which is 3 to the -2nd. And I just have x equals -2. So that means that the log base 3 of 1/9 is -2. Log base 3 of 1/9 is -2. So that's how we'll evaluate logs right now. If it's something that we can evaluate, we're going to switch over into exponential form and turn it into something we know a little bit more about. A lot of times we're dealing with logs. We don't actually deal with the log. We switch it to exponential form because it's so much more familiar to us, and we deal with it that way. Wonderful. Find x. Let's find x. We've got 2 equals log base 3 of the square root of x minus 1. Find x is like solve for x. Again, if you don't know what to do because it's log, switch it over to exponential form. So I'm going to take my base, which is 3, to the exponent, which is 2, and set it equal to the square root of x minus 1. You know what I was just thinking? I think part of the problem with that students have with converting between logs and exponentials is that they had this log here, and now all of a sudden it's on. And so it seems like something's missing. They're like, wait, I converted, but something's missing. It's not. You just have to get over that hump in your mind that says something's missing. All right, now I've got 9 equals the square root of x minus 1. If I want to solve for x here, I can square both sides to get rid of the radical. When I do that, I have 81 equals x minus 1. Add 1 to both sides, and you get x equals 82. That's it. All right, now in order to evaluate logarithms more completely, we're going to talk about these basic properties for logarithms. They're immensely useful to us. The log base b of b is 1. So that means like the log base 3 of 3 is 1. Now, that's going to work the same way for log base e, which is a natural log. ln e is 1. The log base b of 1 is 0. And that's because b to the 0 power is 1. A real number to the 0 power is 1. If you want to see that in exponential form, it looks like that. We could have written this the same way. B to the first is b. B to the 0 is 1. Now, log base b of b to the x is x. All that means is b to the x equals b to the x. B to the x equals b to the x. Now, b to the log base b to the x, b to the log base b of x is also x. That one looks more confusing when I write it out, so I did not write that. But we have the same property. Sorry, I should have filled this in. ln of 1 is 0. The same reason, ln e to the x is x, and e to the ln x is x. Now, notice that these are just, these last two are inverse properties of exponential and log functions. So it's kind of like the undoing you think about when you talk about inverse functions. It's like if I have an exponential function and I apply a logarithm to it, it's sort of like the logarithm undoes the exponent and just leaves you with what you had left, which was the x. It's the same idea in this case. But e to the natural log of x is x. So again, you take e to a log and they sort of undo each other, and all you have left here is this x. This is going to be really important to us when we start to solve these exponential and log equations. And when we're talking about finding critical numbers, let's say you get to a derivative, you have to set one of these equal to 0. You're going to need to use these properties to be able to solve those equations. More properties of logarithms. So again, these are from college algebra. They're going to be very, very important to you here. One of them is that product property for logarithms. So if you're multiplying inside your logarithm, you can split this up into a sum. So this would be log base a of x plus log base a of y. Now, it's really important that we understand that this does not equal log base a of x plus y. So what I have happen a lot of times, and this happens even in higher levels of calculus, students think that because this is the sum of two logs, it's almost like you can just like distribute the logarithm. You can't distribute it. This is a special property for logarithms. It does not work when you are adding inside the log. It only works when you're multiplying inside the log. We can do something similar though for quotients inside logarithms. You can turn it into subtraction of two logarithms. And again, this is not equal to the log base a of x minus y. Not the same. So don't do it. These are the ones that you can do. As far as taking your inside argument to a power, what you can do is you can use this power rule to move the power in front of the logarithm. That's going to be especially important to help us solve log equations. Oh, and I have a note here that I almost was going to forget about. Log base a of x to the mth power is not equal to times log base a of x. Don't do this. So this is like a big no. How do I have no red pen in here? I want to call this out as like a don't do this thing. Excuse me. It's important enough that I need to find the red. We can box it off and say like, nope. All right. I only have a checkbook. We have red, okay? Don't do this. This is like a big no. Okay. Wonderful. Oh, the caution note. I'm getting ahead of myself here. The caution note is just the same thing I just stated, which is log base A of x plus or minus y does not equal to log base A of x plus or minus log base A of y. So same thing I just said, but important enough to repeat. If you don't want to write it twice, that's fine. Didn't work that way. You can't do it. Don't even try. Don't even try. Use properties of logs to expand the expression. So we're going to use those properties we just talked about to expand an expression. Super useful for us all the time in math. When we're working with logarithms, we can simplify an expression. If I was trying to take, here, let me write this down, and then I'm going to say something that's going to maybe upset you. Sorry. I don't, the math teacher always has to say things that upset people. I mean, it just comes with the territory. I'm going to be upset with people. It is what it is. Let's say I asked you to find the derivative of this. Now, at this point in time, you're like, I didn't know how to find derivatives of log functions. That's right. You don't. You're going to find out really soon. But look at how messy this is. If from what you know about derivatives, you're thinking like, okay, quotient rule, chain rule, I got all kinds of crazy stuff going on. I mean, let's not even think about all the variables that are occurring here. But it would be messy. I mean, even if these were all x's instead of x's and y's and z's, you'd be like, oh, this doesn't look good. You'd want to simplify this. We're going to do that using properties for logarithms. The first thing I'm going to do is break up this quotient into the difference of two logarithms using that quotient to difference rule. So we're going to say that this is the natural log of the square root of x squared plus y squared minus the natural log of, in parentheses, z minus 1. I don't want to lose the minus 1, so make sure you put parentheses around that. Now, I'm going to rewrite the first term, x squared plus y squared, to the 1/2 power. Running out of space here. Now I can use this power rule for logarithms, pull that 1/2 power out and move it in front of the expression. I'm going to rewrite this now as 1/2 ln x squared plus y squared minus ln z minus 1. That's it. Stop. You can't do anything else. We've completely expanded it. This means that you're done. Stop. Don't try to do anything else. What students will sometimes do is they'll be like, I think I can split this up into the ln of x squared plus the ln of y squared. No, you can't. Because you can't do that. You cannot do that. All right, so if you have a sum or difference inside your logarithm, there's nothing you can do about that. And as far as these squares on the x's and y's, there's nothing you can do with that either, because the square is not being applied to that whole expression. It's being applied on each variable individually, and you can't pull those apart. So this one's done. Stick a fork in it. All right, we're going to use properties of logs now to condense an expression. So we're going to go the opposite direction. I have log of u. By the way, this wasn't mentioned, I don't think. And now I'm trying to figure out, was this mentioned? It was not mentioned. I'll write a note off to the side here. If you just have log x, for instance, that is assumed to be log base 10 of x. So this note, I don't know how I did not mention this sooner. if there is a log and you don't see a base on it, it's assumed to be log base 10. And I think that bothers students because they think that if there's no base, it's assumed to be 1. Because if you just see x, you think it's 1x, but it's not the same. If you just see logarithm, it's assumed to be log base 10. Log base 10 also has a lot of applications, just like how the log base e has a lot of applications. So it's generally shortened to just log. So you're not seeing any sort of base here on your logarithm. It's assumed to be 10. I just wanted to make sure to give you that note so that you understand. You've probably seen that before, but maybe it's been a while. All right, minus 3 log v plus log u plus v. All right, now we're going to condense. So what we're trying to do is take these logs and turn them into one big log. So in order to do that, we're going to go through and simplify this. One of the things I'm going to do first is I'm going to work backwards to undo these constant multiples. I don't want this constant multiple on here. So I'm going to rewrite this as log v cubed. Sorry, that's a v. I don't know why it looks funny. Could not tell you. Okay, and then we'll just sort of move in order and simplify these logarithms from left to right. So if you have log of u minus log of v cubed, we'll say that this is the log of u over v cubed plus the log of u plus v. And now we can combine these two logarithms. The first two we combined using a quotient, and the next two use addition between them. So we'll combine them using a product. So this will be log u times u plus v divided by v cubed. I mean, technically this is probably fine. You could also write this as u squared plus uv divided by v cubed. I don't know, I actually almost like the first variation better. If we're talking about condensing, I don't know, I feel like factored is more condensed, but who knows? But this is how we would write this as one logarithm. I should probably put some parentheses around this, or brackets in this case, just because there's a lot going on. Any parentheses would have been fine here. This one's already got parentheses, which is why I went with brackets. But that's how you would condense your logarithms. Use properties of logs to evaluate the following without calculator. You know, anytime we're not using a calculator, it makes me really happy. So let's do that. Log base 5 of 100 minus log base 5 of 4. That would be the first one. All right, so in order to evaluate, we're going to have to use properties of logs. What I would do right now, if I were you, is because you see subtraction between your logarithms, you'd probably go ahead and combine these using a quotient. Sometimes you can try different things. If you tried this exponential form, though, you'd be like, wait, 5 to some power is 100, 5 to some power is 4, and be like, I have no idea. So the best thing you can do is switch this over to be a quotient inside your logarithm. And now we have the log base 5 of 25. And now this is something that we can figure out because we can use the exponential form to determine this. I know that 5 to some power is 25. So that means the power that we're looking at is 2. 5 squared is 25. So the log base 5 of 25 is 2. We'll do another one. This one looks funny, but we'll evaluate it down to something a lot more simple. This is 7 to the power 1/2 log base 7 of 9. So 1/2 log base 7 of 9 is all in the exponent. The first thing I'm going to do is I'm going to take this power I'm going to take the constant multiple from the front of the log and move it onto the power inside that log argument. So this will be 7 to the log base 7, 9 to the 1/2 power. You know, there was a lot going on here exponent wise. 9 to the 1/2 power is the square root of 9. So this is 7 to the log base 7 of 3. And we had a rule for that. It's not one that stands out as much to students, but it looks like this. B to the log base B of x is x. We can use that here to simplify to 3. All right, what's that? Now, I was talking about the change of base formula. So let's talk about change of base formula. I was saying, how could we evaluate these in our calculator? There's no button to input something like log base 5 of 100. Well, the change of base formula says that we can change all of our logarithms to either have a base of 10 or a base of b. So the change of base formula it says that log base b of x, we can rewrite as log x over log b, so the quotient of two logarithms. And these are log base 10. Or you can switch these to natural logs. So it can be the natural log of x over the natural log of b. Now, a lot of times when you write natural logs, you'll see them actually written in script. We don't usually write ln by hand anyway, just because sometimes the L, I think, looks like a 1. You don't really have that problem when you're writing out log, but when you're writing ln, we usually just write it in script, but it does not matter as long as you can read your own writing. But this allows us to change our logarithm from a log base b to a log base 10 or a log base e. And that's a good thing for us because these are buttons we have in our calculator. So I can take a log that I'm not really sure how to enter, and I can rewrite it as something that I can enter in my calculator. So for instance, if I was trying to find a log base 3 of 50, I can rewrite it in my calculator in 2 ways. I can say that this is the log of 50 divided by the log of 3, and I'll get an approximation for it. Now, we're going to be really careful with our parentheses here when we enter something like this into our calculators. So let's say I wanted to enter the log of 50. I'm going to make sure I close off that parentheses before I divide by the log of 3. And I get approximately 3.561. Of course, it's not exact, but it's close. Now, this will give you the exact same approximation if you use the natural log instead of the log base 10. You can pick either one. Going back to our calculators now, I can hit this natural log button. I'm sorry, I didn't show you what button I was hitting earlier, but the log is right there. The natural log is the one below it, ln. And I can say ln 50, close my parenthesis, then divide by ln 3, and I get the same exact approximation that I got before. So this is about 3.561. That's how you would use your calculator to evaluate a log. So you're asking yourself 3 to what power gets me to 50? Well, you know that 3 to the 3rd power is 27, and 3 to the 4th power is 81. So it makes sense that the exponent that would get you to 50 would be somewhere in between 3 and 4. So maybe if you wanted to note that 3 to the 3rd is 27, 3 to the 4th is 81. So your value is in between those two exponents, which makes sense because 50 is between 27 and 81. Okay, so it does make sense, and that's what the value represents. You know, I was just thinking, I'm wearing this striped sweater, and these guys are also wearing stripes. That was not planned. Okay, graphs of log functions. We're not really going to spend a whole lot of time talking about this. Recall from the opening example that y equals log base a is the inverse of y equals a to the x, which has this graph. Or my arrow went to the wrong one. You know, I just need like a lot more white out in my life. You know that? You know that. You know that better than anyone. Okay. I don't know. Just gonna make it all make sense. Good. Also recall that inverse functions, when graphed, are reflected about the line y equals x. So you can kind of see that here in this little graph. You can see this dashed line at y equals x. The function f of x is the one in red. You see kind of moving along like this. Its inverse is reflected over that line. So all of the points from one graph, you can reflect across the line to get to the points on the other graph. So that's just one property of inverse functions, that they're reflected about the line y equals x. So if you're thinking about y equals a to the x, its inverse function, log base a of x, this is what the graph would look like, and it's reflected about that line y equals x. So all of the points from this exponential graph and the log graph are going to be equidistant from this line y equals x, about which they are reflected. So that's what the graph looks like. So, you know, we spent a lot of time in the last section looking at a to the x and what happens when we shift it and change the value of a and make a less than 1 or make a greater than 1. If you're trying to graph a log graph, you're just going to have to take the inverse of the exponential just by graphing it or reflecting it about the line y equals x. That's the way we would graph that. You could always graph it in your calculator using the change in base formula if you want to do that also, but I'm not going to be doing that with you. That's something you should have done in college algebra, and it's not really a focus that we're going to be working on here, but it's something worth mentioning for sure. All right, what we are going to do here is we are going to solve equations where logarithms will be necessary for us to solve. So let's go ahead and start solving some equations. The first one is 3 times 5 to the x minus 2 plus 1 equals 10. Now, you might be looking at this and thinking like, I thought you said we were solving log equations. We are going to be talking about solving log equations, but we're also going to be talking about instances where we need to use logs to solve exponential equations. Now, if you're looking at these instructions above, notice that number 1 is something that we did in the last section. We talked about how we would set the bases equal to each other and then solve for the exponent, which we had the bases equal. If we can't do that, which we're not going to be able to do in this section today, we're going to start by isolating the exponent. And then we're going to have to take logs on both sides to isolate the variable, or to get the variable out of the exponent. That's going to be the key here. You're not used to dealing with situations where we have a variable in the exponent. We got to get it out. And that's the whole purpose of the log. And you'll see how that works. The first thing I need to do is isolate the expression that has the variable in it, which in this case is 5 to the x minus 2 power. So to do that, I'm going to leave the exponential expression by itself for now, and I'm going to subtract 1 from both sides. So when I subtract 1 from both sides, that leaves me with 9 on the right-hand side. Now, to get the exponential expression by itself, I'm going to divide both sides by 3. So 9 divided by 3 is 3. So the first step was subtract 1, and the second step is divide by 3. Just like you're solving for x in a regular old linear equation, it's just that now we don't really have a linear situation, but we've isolated the variable expression. Whatever you do, don't try to add 2 on both sides because it's in the exponent, not really 2. It's in the exponent. You can't touch it. In the last section, we would have had something on the right-hand side that maybe had 5 as a base, like maybe 1/5 or 1/25 or 25 or any value that we could somehow turn into a base of 5. Well, we can't take 3 and turn it into a base of 5, and that's where we're going to have to use our logarithms. Now, step 3, because we did step 2, isolate the exponent, by isolating the exponent. We're working on it. It says to take either the natural log or the log of both sides. If there's a base of e, always use natural log. If there's a base of 10, always use log. But these choices will make the work easier. It kind of depends. You don't have a base of 10, so it's kind of up to you if you want to use a log or a natural log. Personally, I use a lot of natural logs just because it's just what we use more as you get into higher level math classes. We don't use a lot of base 10 logs. So the only time I use a base 10 log is if my base is 10. My base is 5. So I'm just going to use a natural log. So let's go ahead and we're going to take the natural log on both sides. So I'm going to say this is the natural log of 5 to the x minus 2 on the left and the natural log of 3 on the right. And if it seems like a really strange thing to do, if you're like, why the heck did we just do that? Well, it's because we have this power property for logarithms that says that I can take the power and move it in front of the logarithm. Once I have a log on it, it allows me to take this x minus 2 out of the exponent and pull it up front. That was the whole goal. I can't have a variable in the exponent and solve for the variable. I need to pull it out using a logarithm. All right, now that we have it out of the exponent, we can solve for x. The way that you're going to do that is by dividing both sides by the natural log of 5. And then adding 2 to both sides. So we have ln 3 over ln 5 plus 2. I feel like a lot just happened in this example. This should be something that you covered in your prereq, but a lot just happened. We need to make sure that we apply these steps in the right order. So we isolated the variable term. Once we did that, we were able to apply a natural log on both sides, bring the exponent down, and then we solve for x using traditional methods. This, I think, approximates to like 0.2638, but I'm going to go through this with you just to make sure that you understand how to do this. So we're taking the natural log of 3, parenthesis, divided by the natural log of 5, parenthesis, plus 2, and you get about 2.683. Please don't approximate these unless I specifically ask you to in the directions. I always like answers to be exact. So you might not like this answer. It might look terrible to you, but it's the exact answer with all of its precision. This 2.683 is just an approximated value. So unless I ask you to approximate your answer, please leave it exact. All right, so that was one example. All right, wonderful. The next example, let's find. There we go. So this one is 2. Oh, it's example 2 also. E to the 3/4 x minus 6 equals 4. So the x is in the exponent again. That's the whole reason we're going to be needing logarithms here to solve this equation. Anytime you see the variable in the exponent, you know to get it out, you're at some point going to need a logarithm. And again, we're going to isolate the term that has the variable in it. So I can add 6 to both sides. So we added 6 to both sides, and then we're going to divide both sides by 2. And you end up with e to the 3/4 x equals 5. Now, your instructions said that if your base was e, you should definitely be using a natural log. And I totally agree. You want to be able to get this answer as simplified as possible. So make sure that you're using natural logarithm if your base is e. And you know, you can always use a natural log on both sides, but especially if your base is e. So I'm going to apply the natural log to both sides of this equation now that we have the variable term isolated. And now we can use a property for logarithms. If you don't remember it, I'm going to remind you of what it was. It was the natural log of e to the x was x. Now, you don't have just x, you have 3/4 x, but we're going to use the property, the undoing or the inverse here to pull that 3/4 x out. So the natural log of e, just writing this off to the side, to the 3/4 x is 3/4 x. Okay, so we're going to use this property now because we had a base of e and we use the natural log to simplify. Now we can use that property. So now I can say 3/4 x equals the natural log of 5. And then to isolate x, we can multiply both sides by 4/3 to get x by itself. 3/4 times 4/3 is 1. So do this. This is our exact answer. If you were to approximate that, you would get 4/3, not 7/3, 4/3 times the natural log of 5. And you get about 2.146. This is an approximated answer. So only give me that if I ask you to approximate. All right, last one. Yes, the last page here is blank, and it's going to stay blank. So if you were like, oh, we have a whole page after this, actually we don't. I'm on the last example. You're up. It's going to be all right. Although personally, I feel like this section just flew by. It just flew by. I don't know how long it's been, but it seems like 5 minutes. Does it seem like that to you? It does, doesn't it? We're going to let C of t equals 0.8. Oh, no, 0.08. Oh, I'm putting this white out to work here today. 0.08 times 1 minus e to the negative 0.02 t. Okay, so C is equal to 0.08 times 1 minus e to the negative 0.02 t. We're going to let this function give the concentration of a drug in the bloodstream at time t. How long until the concentration reaches 0.02 grams per centimeter cubed? This application is actually going to pop up quite a bit as we work through this chapter, but every time you see it, it's going to be asking you for different stuff. Now, notice that this is just asking you about the concentration. Remember when we talked about derivatives and we were like, okay, well, now this is asking you for one thing, and the next question is asking you for the change in a quantity. So when you see this again, it might be asking you for the change in the concentration, in which case you'll be like, oh, wow, I'm like really deep into these derivatives now in section 5.5. I should know how to do this, which is true. You will in section 5.5. But right now, we're just going to be talking about the actual concentration being 0.02 grams per centimeters cubed, and we're being asked to find how long That's your question. How long? That means find t. Remember, the question always gets you to the variable that you're looking for. So if you're not sure, just like, ooh, I don't know, what is it asking? Oh, how long? That means solve for time. You're being given a concentration in this case. If CT is the concentration, you want to know when C of t is equal to 0.02. So you're going to say 0.02 equals 0.08 times 1 minus e to the negative 0.02 t. And we're going to solve for t. In order to solve for the variable, I need to isolate the variable term first. That means anything that's not in the variable term, I have to get rid of it. I have to undo it. This 0.08 is getting multiplied into this expression. To multiply it in, just divide it out on both sides. We don't need it. We're trying to get this variable term by itself. So I'm going to just divide it out. And then we'll simplify. Okay, so now we have 0.02 divided by 0.08 leaves us with 1/4 equals 1 minus e to the negative 0.02 t. Okay, we're getting there. We see the light at the end of the tunnel. If I want to get this expression by itself, I can subtract 1 from both sides. And then I get negative 3/4 is negative e to the negative 0.02 t. So we just subtracted 1 from both sides of the equation. If this is driving you crazy, like it's driving me crazy, I don't want to have a negative on both sides. I'm just going to multiply both sides by -1. And I have 3/4 is e to the negative 0.02 t. And I'm still trying to get t by itself. So what I'm going to do is I'm going to apply the natural log to both sides now, because now all I have left is this variable term with the variables in the exponent. So I'm going to apply the natural log to both sides of this equation. And then we're going to use that property that says that natural log of e to the x is x, because the natural log is undoing the exponential expression. So now I can say that I have the natural log of 3/4 is equal to negative 0.02 t. Now I can solve for t by dividing both sides by negative 0.02. So I'm going to take the natural log of 3/4 and I'm going to divide it by negative 0.02. And I'm going to get a value for time. And this time we need to discuss here, but now we at least have a number and it's positive. So that's good because we know time can't be negative. So my exact answer is going to be ln 3/4 divided by negative 0.02. We just approximated that to 14.38-ish. Okay, but let's talk about our unit here. Oh, another thing we should mention too, what's kind of interesting, we took the natural log of 3/4 and divided it by a negative number, and we got a positive number. So that means the natural log of 3/4 is actually a negative value. If you're taking the natural log of a number that's between 0 and 1, it's going to come out negative. The natural log of a number that's greater than 1 is going to be positive. So maybe I should note that. ln 3/4 is less than 0 because 3/4 is less than 1. This reminded me of one more thing I want to remind you of in a second, but hold on, let's finish this problem. We have the concentration of drug in the bloodstream. How long until, oh, you know what, I didn't actually tell you the unit. It's minutes. I should have put that in there. But first of all, even if I didn't give you a unit, let's use some common sense here. Well, maybe there's no common sense to be used. I was going to say, like, it's probably not going to happen at 14 seconds, but how do you know? Like, this doesn't mean much to us as non-medical drug people. Like, I don't know what kind of concentration this is. Is it a lot? Is it a little? I don't know. So maybe it would be 14 seconds. Let's see, at time t minutes. Add that to the problem so you at least know where that came from. All right. Anyway, all right, that's what I wanted to say about this application. One more thing I want to say, though, before I let you go. I would be remiss if I didn't make some connection here between these two graphs, and it probably should have been done here. When we talk about inverse functions, we talk about their domains and ranges being switched, and I want to make sure we say something about that. Domain of y equals a to the x is all real numbers. I can evaluate this at any value of x I want, and it's going to give me an output. I can take a number to any power I want and get an output back out. But the range in this case, by the way that this function is defined, covers values from 0, not inclusive, up to infinity. So you can see how if I'm taking a to a power, if a is greater than 1, then I only have the values for y here being defined as positive values. So I'm taking some number to a power, and even if the power is negative, it doesn't matter, because a negative exponent just means that now I'm taking a reciprocal, basically. So it doesn't change the sign of the output terms. As far as your log function, remember that for an inverse function, the domain and the range switch. So here, I would say that the domain, this is actually really important because this is going to matter to you as you're working on these functions in later sections. The domain of y equals the log base a of x is just trying to figure out what value of x can we possibly use. Well, in this case, we can only use values of x that are positive. Logarithm isn't defined for values of x that are negative or even 0. So in this case, we would say that the domain of this function is the same as the range for y equals a to the x. It's from 0 to infinity. And you can see this represented on the graph. Our log function only covers positive values. And we would say that the range of y equals log base a of x can cover any real number. So it's going to be the same as the domain of your exponential function. I didn't want to not mention that you cannot take the log of 0 and you cannot take the log of a negative value. So if you're, that would end up giving you some domain issues here. The logarithm itself, though, can be represented by a negative number. You can see that the graph does go negative, but you just can't evaluate it as a negative number. So that example I just went through, we said that the natural log of 3/4 was negative. Well, yeah, because 3/4 is less than 1. So if you're looking at that value, the natural log of 3/4 was about right here. I know. So there's a lot to say here. Again, it's all stuff you should have learned about in your pre-req, but since we are going over this, because it's going to be important to us in the chapter where we're reviewing it all, I really wanted to make sure to mention that because it is very important to us. All right. So your exponential function only exists for positive values of y, and your logarithm only has a domain for positive values of x. That's good. All right. Was that all I wanted to say? Oh, I couldn't let you. I was gonna think about it all day and be so upset. So I'm glad we went back to that. All right, so that's what I had to say about logarithms and exponential functions. I'm going to verify that my last page is blank and there was nothing else I was supposed to do there. It appears that that is the case. All right, that's it. We're good. That's all I got for you. Practice your logs and your exponential functions. And remember, we're skipping section 5.3. It's not required for our class. So when we come back in section 5.4, we'll talk about finding derivatives of exponential functions and then talking about how to apply those derivatives to do all kinds of interesting things like, I don't know, find critical numbers and maybe find points of inflection, and we'll maybe talk about implicit differentiation having to do with exponential equations. Anything that we did in chapter 4 and chapter 3 is fair game. We're going to be doing it all over again with exponential and log functions. So you have that to look forward to. Let me know if you have any questions. Have a wonderful rest of your day.